Welcome to Boson Buzz, where we dive into the coolest scientific ideas and breakthroughs shaping tomorrow's world. Our modern world is built on a promise of portable power. From the smartphone in your pocket to the electric car on the highway, we demand more energy for longer durations from increasingly smaller and lighter packages. This promise is made and kept by the battery, but we are now hitting a fundamental physical limit. Today's advanced lithium-ion batteries represent an incredible engineering achievement, yet they carry a heavy inherent burden. A significant portion of their weight, size, and cost comes from the fact that they must contain all the internal chemicals required to create the electrochemical reaction that generates electricity. They are, in essence, sealed boxes of potential energy. This is why an electric car's battery pack is so massive and expensive, and why your phone can barely last a single day under heavy use. We are essentially packing as much energy as we possibly can into a closed container. But what if the battery didn't have to contain one of its most critical ingredients? What if it could simply breathe it from the infinite and free resource that surrounds us all, the air we breathe? This is the brilliantly simple yet powerful concept behind metal-air batteries, a true paradigm shift in energy storage philosophy. Unlike every conventional battery, from the lead-acid battery in your car to the lithium-ion pack in your phone, which are all closed, self-contained systems, these batteries are fundamentally open to the environment. They embrace the world around them as a key part of their operation. Inside, they use a solid metal like zinc, aluminum, or in its most advanced theoretical form, lithium, as one of their core electrodes. This metal acts as the fuel. But instead of also containing a second heavy, complex chemical compound to react with this fuel, the design is elegantly minimalist and resourceful. It pulls in oxygen directly from the surrounding atmosphere. Oxygen acts as the second key reactant, the cathode. Think of it like the difference between a candle burning under a sealed glass jar and a candle burning freely in an open, well-ventilated room. A regular battery is the sealed jar. It has a finite amount of oxygen trapped inside, and once that is consumed, the flame dies, its energy depleted. A metal-air battery is the open candle, constantly drawing in fresh, new oxygen from the infinite atmosphere to sustain its flame and continue its chemical reaction indefinitely, or at least for as long as the metal fuel lasts. This one simple architectural change, creating a battery that breathes, unlocks a staggering potential for energy storage, because the most important and heaviest ingredient for power is now all around us, completely free, utterly abundant, and doesn't need to be carried along for the ride. So, how does this simple act of breathing air translate into electrical power? The process is an elegant dance of chemistry and engineering. The battery features a special air electrode, which is not a solid plate but a sophisticated, porous membrane that acts much like a lung. It is designed to allow oxygen molecules from the air to flow freely into the battery's core. Inside, that oxygen reacts with the metal electrode, which is slowly consumed or oxidized in a highly controlled process that generates a flow of electrons. This is the electricity we use. Because the battery doesn't need to carry its own internal oxidizer, it can achieve a theoretical energy density that is 5 to 10 times greater than the best lithium-ion batteries available today. For the same weight and volume, you could get 5 to 10 times the power. This isn't a minor incremental improvement. It is a quantum leap that could completely redefine the limits of portability, range, and endurance for our machines and devices, effectively ending the constant anxiety of a dying battery. The implications of this leap in energy density are profound and far-reaching, promising to untether our technology and our society from the power grid in ways we can only begin to imagine. For transportation, this technology could be truly transformative, enabling electric vehicles that can travel 1,000 miles or more on a single charge, effectively eliminating range anxiety forever. This would be possible with a battery pack that is far lighter, cheaper to produce, and mechanically simpler than today's complex and heavy lithium-ion systems. This incredible power-to-weight ratio could finally make electric aviation a practical and widespread reality, powering everything from small commuter planes and air taxis to long-endurance drones, all with clean, efficient, and incredibly dense energy. In our everyday personal lives, it could mean a world where personal electronics like laptops, tablets, and phones run for weeks or even months without ever needing to be hunted down and plugged in, fundamentally changing our relationship with power outlets and charging cables. For renewable energy on a grand scale, massive stationary metal air batteries could store excess solar and wind power for days or even weeks on end, providing reliable, long-duration backup for the electrical grid and making a fully renewable powered world a much more feasible goal. It promises a world less tethered, where the constant low-grade anxiety of a dying battery indicator becomes a quaint memory, and our primary energy source for portable power is as ubiquitous, invisible, and reliable as the air itself. Of course, a system that breathes is also a system that is inherently more vulnerable. The main challenge that has historically plagued metal air batteries is their longevity and reliability. Because they are open to the atmosphere, moisture and other impurities from the air, such as carbon dioxide, can contaminate the sensitive internal chemistry. This can cause the battery to gradually degrade, lose efficiency, or even fail prematurely by clogging the delicate air electrode. Recharging these batteries has also been a significant hurdle, as reversing the chemical reaction is more complex than in a standard lithium-ion cell. However, researchers are now making groundbreaking progress by developing new, highly selective catalysts and advanced multi-layered membranes. These membranes act as sophisticated, intelligent filters, allowing life-giving oxygen to pass through while actively blocking harmful water vapor and contaminants. We are, in effect, teaching these batteries to be more resilient and selective in what they breathe, enhancing their durability and bringing them closer to practical, everyday use. While a mainstream, rechargeable lithium-air battery for your smartphone may still be a number of years on the horizon, the broader technology of metal air chemistry is already quietly and reliably powering specific parts of our world in crucial niche applications. For decades, smaller, simpler zinc air batteries have been the undisputed standard power source for hearing aids, where their exceptionally high energy density and long, stable shelf life are absolutely invaluable, allowing for devices that are both tiny and long-lasting. In larger, more industrial formats, zinc air systems are being seriously explored and tested for grid-scale energy storage, where their potential for very low cost, high capacity, and inherent safety presents a major advantage over some other technologies. The progress in research labs around the globe is accelerating at a remarkable pace, with new material designs, novel catalysts, and innovative electrolyte solutions systematically solving the historical problems of efficiency, rechargeability, and longevity one by one. Each scientific paper and each laboratory breakthrough brings us incrementally closer to the day when the severe limitations of our current battery technology will seem as archaic and frustrating as the limited battery life of early mobile phones now appears to us. The foundation for a true energy revolution is being meticulously laid brick by brick for an energy storage solution that is not only vastly more powerful, but also more in harmony with our environment, elegantly drawing its fundamental strength from the very air we move through every day. We are standing at the precipice of a fundamental and necessary shift in how we store and think about energy for our mobile and renewable future. The battery that breathes represents a decisive move away from closed, resource-intensive, and chemically complex systems towards elegantly simple, open, and sustainable ones. It is a profound testament to human ingenuity, demonstrating our ability to turn the very atmosphere that surrounds us into an active, limitless component of our global power infrastructure. This technology, once fully realized, promises to unlock a new era of mobility and autonomy, powering our vehicles, our devices, and our grids in a way that is quieter, cleaner, and far less constrained by the physical and economic limits of current energy storage. We are learning to harness power not by building bigger containers or mining rarer materials, but by designing fundamentally smarter systems that interact intelligently and synergistically with our world. The ultimate future of portable and stationary power may not be found in a deeper mine or a more complex and volatile chemistry, but in the simple, profound, and timeless act of drawing breath, allowing our technology to run efficiently and cleanly on the most abundant and accessible resource on planet Earth. If you found this as fascinating as I did, do me a huge favor and hit that like button. Share this video with anyone who loves science or just cool, futuristic tech. And of course, if you want to stay updated on this and other amazing breakthroughs, make sure you subscribe to the channel. Thanks for watching, and I'll see you in the next one.